Welcome everybody to this short video. In this video, I would like to talk about something regarding the linear transformation and matrix transformation. So you can look at the page here. I gave you the definition of a linear transformation here. It is an abstract definition, and um, by transformation, basically, we are saying that there's something called domain. You are mapping something by the map T, we call it transformation, to a codomain. Yeah. There's something I would like to explain regarding domain and codomain. In this particular case, I use the notation Rn to represent that I'm talking about the n-dimensional space, meaning that each element here is a n-dimensional vector. Yeah. And you can think of it as a column vector. That's the more convenient notation. Then after the map T, it is mapping a vector in the domain, which is n-dimensional, to a codomain where the dimension may be changed, right? And in this case, I'm using the notation M to call it m-dimensional space. And after the map, I'm saying that if you have a vector V, you are mapping by the map T to T of V. This vector itself now is inside the codomain, which must be an m-dimensional vector. Yeah. So I hope you see what I mean by the dimensional changed. Yeah. And in such cases, because we are only concerning about the linear transformation, so the keyword is linear. And the fact is that I don't want to get into the details, but just to let you know the fact, which is that any linear transformation can be represented as a matrix transformation. So I would like to explain more. Can be represented as a matrix transformation. So what do I mean is something like this. And let's drop this topic a little bit. Let's say I'm not talking about linear transformation for now. And if, just as an example, if now I give you a matrix A, let's call the matrix something like 1, 2, 3, 4, 5, 6. And the size of the matrix is 2 by 3, right? Because there are 2 rows and 3 columns. And I claim that any matrix automatically defines a linear transformation. So the note is like this: A defines a linear transformation. So what I mean is something like this. We can use the matrix multiplication to take a look at this. For example, if I take the vector V as, let's say, 3, 0, 1, and what I meant by this linear transformation is actually like this. We can look at the matrix multiplications. Now the matrix multiplication is a valid one because you are taking the multiplication row by column, something like this. Yeah. You see the matrix A is this having the size 2 by 3 and the V has the size 3 by 1. So you see it is a valid matrix multiplications. After the matrix multiplications, it should be a 2 by 1 vector, right? Yeah. So if you remember the basic matrix multiplication, you see what I mean by this. Now, what I mean is something like this. Now let's look at the domain of this transformation. The domain now must be a vector which is 3 by 1 if you view it as a matrix, because for the matrix multiplication to be well defined, we need that the number of columns of A must be the same as the number of rows of the vector V, right? So it means in this case the domain must be R3. Yeah, because we need a vector which is three-dimensional for this matrix multiplication to be well defined. Now, what is the dimension of this vector? And I've talked about it already. Because this vector now, after taking the matrix product, it must be 2 by 1 in terms of the size of the matrix. It essentially means that it is a two-dimensional vector after taking the transformation. So it means what? The whole thing essentially means that this is a map So the matrix, which has the size 2 by 3, is defining a linear transformation mapping the domain R3 to R2. Do you see my point here? The fact is that the dimension of the domain and the codomain is actually defined by the size of the matrix A. Yeah, please take a look. Please think about what I mean by this. And then we'll see more examples now. Let's take a look at the question I posted here. Let's say now I'm giving you another matrix where the size is 4 by 8, meaning it has 4 rows and 8 columns. And are you able to tell me what is the dimension of the domain and the codomain? And if you understand the logic in the last page, we need the fact that this vector v to have the size 8 by 1 because basically we are doing matrix multiplication, right? To get to the codomain. And this matrix multiplication is only valid when you are looking at the 4 by 8 matrix times an 8 by 1 vector. And it means that the domain must have 8 dimensional. Yeah. And then after the matrix multiplications, we'll be getting to the codomain. So what is the dimension of this vector? So please take a look at the matrix product. The matrix product will get a vector 4 by 1. Essentially, it means that the codomain must have dimension R4, right? So it's just a basic exercise to check whether you understand what I mean by the matrix, any matrix, actually define a linear transformation like this. Yeah, and obviously I didn't really do the mathematical check to check step by step that this one is actually linear transform, but just to let you know this fact is true. Yeah, so and the fact is that any transformation defined this way by using the matrix multiplication of A must be a linear transformation, which means it must satisfy the 3 definitions that I posted in the last page. Yeah. Yes, so actually in reverse, what I said was also correct, which is the fact that if you are given any linear transformation, we should be able to find a standard matrix such that we can represent the given linear transform by using the matrix A. I kind of like the matrix multiplication I talk about. Yeah, so up to now. Now, please look at the current exercise. I give you a transformation like this. You don't have to check that it is linear. It is actually linear, and it is actually quite easy to see why it's a linear transformation just because of the fact that if you look at the vector in the codomain, every entry is a linear combinations of the variables x1, x2, x3. When you notice something like this, where in the codomain each entry in the vector is a linear combination of x1, x2, x3, then it must be a linear transformation. And let's get back to our central question, which is the fact that are you able to find a matrix such that this transform is actually equal to the transform defined by the matrix A. So what I mean is that are you able to find a matrix A such that you do a matrix product like this, you'll get to the codomain in this form. Yeah. So now, first of all, let's do a dimension check. This map is T mapping from a 3-dimensional vector to a 3-dimensional vector, right? So it gives you a sense that for the whole thing to make sense, the A must be 3 by 3 because when A is 3 by 3 first, the matrix product is valid. Second, after the matrix product is done, the outcome of the vector must be 3 by 1, right? So basically, this problem is asking you to search for a matrix A, which is 3 by 3. Yeah. So how to do it? You have to compute these 3 vectors. Yeah. So basically, we care about these 3. Or essentially, basically, you have to compute these 3 things. Yeah. You can do the computation now. Then you will see that. And the computation essentially means you're setting x1 be 1, x3 be 0, x2 be 0, right? So basically x1 is 1 now, x3 is 0, this is always 0, x1 is 1. So it means you're getting a vector like this. And the second one, you see x2 is 0, and the other spot is always 0. So you see you're getting a 0 vector. And the last one is 0, x2 is 0, only x3 is 1, right? So it means you are getting something like this. Yeah. Now, you can memorize it this way. The fact is that you can think of it as the column 1 of the matrix A. This one is the column 2. This one is the column 3. It always like this. It always like this. And it means that the matrix A that we are looking for, we have obtained the column 1, 2, 3 already. Yeah. Column 1, column 2, column 3. So I put in the numbers one by one. Column 1 and column 2 and column 3. Yeah, so I claim that this is the answer we are looking for whenever we are looking for a standard matrix A to represent the linear transformation. And that's the way to get it done. And in case you want to check, feel free to check it. Now the matrix A, if you multiply to a vector like this, and as a matrix multiplication, you will see that like row times column, you get this. Then row times column, you'll get the second spot, which is 0. Then the last row times the column, you'll get x1. Yeah. So which is the same as our map T, right? Exactly the same. Yeah, and that's a way to get the standard matrix A. Yeah. Please look at the current problem. Do you understand what I'm asking? Such problem can be asked in some other ways. For example, we can directly give you such a transform. You see, this transform is like you are mapping from this domain, x1, x2, x3, to the new set of variables, which is w1, w2. And this is a three-dimensional domain where the codomain is two-dimensional. And same thing, I can ask you to search for a matrix A such that it is a linear transformation defined by the standard matrix A to get it done, where the expressions are given. Yeah. First, please make an educated guess on the size of A. The fact is that it's a 3 by 1 matrix. This is 2 by 1. And for the A to make sense of a matrix product, I think the A must be having the size 2 by 3, right? Because if it is 2 by 3, the matrix product is valid because these two numbers are the same. And after the multiplications, the outcome is a vector which is 2 by 1, right? Yeah. So anyway, the A must have the size 2 by 3. And to search for such a matrix, you can do the same trick as what I said before. The fact is that you have to look at what's happening. 1, 2, 3. And basically, you can do this computation, right? Because the expressions of W1, W2 are given in terms of x1, x2, x3. So when you finish this computation, you will automatically see what kind of matrix you're getting. Yeah, so please do the calculation now. If you have time, pull out a pen and do it. And the W1 is basically x1 plus 3x2, and x1 is 1, x2 is 0, right? So W2 is minus 10 x2 plus 7 x3. Both x2, x3 are 0, right? So it means we're getting a vector, we call it a column 1, 0. And if you recall the last exercise, this one must actually be the column 1 of A. Then you can do the remaining. You will get the column 2 of A and also column 3 of A. And then you'll get the matrix A automatically. So now, if you do the calculations, you'll see that the second column, you will have this. So please do the calculations one by one. And for the last column, you see x1 is 0, x2 is 0, only x3 is 7. So it means you're getting this. So if you combine, the A must be of the form something like this. Must be, yeah. So this is A, yeah, because I'm just copying the column 1, column 2, column 3 into the matrix A, right? And let's look at the next problem. Please look at the current problem. I'm giving you a linear transform such that the three maps are given, yeah, of three different sets of vectors. And I would like to find the matrix A, the standard matrix A, that can be used to represent this linear transformation. Yes, so in this case, what should we do to find the matrix A? And first of all, please do a quick dimension check. Now the linear transformation is sending a three-dimensional vector to another three-dimensional vector. So it's R3 to R3. And basically it means the matrix A, I believe, must have the size 3 by 3 in this case. Yeah. Then secondly, if you follow what we did in the last two exercises, the fact is that the column of A, the column of this A must be basically the same as, for example, the column 1 must be the same as T of 1, 0, 0. The column 2 must be T of 0, 1, 0. The last column must be T of 0, 0, 1. It must be something like this. Yeah. And now, I think the last column is already complete because I'm directly giving you the last column here. Yes, for the matrix A. But please think about it. How can we compute, for example, how to find the values of T of 1, 0, 0? Do we have any idea about it? This vector is not given, but we can do this computation this way. Look at this and look at this. The fact is that the vector 1, 0, 0 is the same as the vector 1, 1, 1 minus 1 minus 0, 1, 1, right? So now because the t is a linear transformation, it means that we can do the calculation this way. Yeah. And please, these two vectors are given, right? So I will just replace the value. T of 111 is the vector 305 minus the second vector is this one, minus 40 minus 1. So now you'll get this vector. So it means that this is what? This vector is the vector for T of 1, 0, 0, which is exactly the column 1 of matrix A, right? This is the column 1 of matrix A. Yeah. So we have got this, we have got this, yeah. And we are left with the middle one. Please think about it. How can we obtain the middle one? Yes, so the middle one is the column 2 of the matrix A. Yeah. How can we compute this? You always have to make use of the given set of values. And please take a look. The vector 0, 1, 0 can be decomposed as the vector 0, 1, 1 minus 0, 0, 1. Yeah. And why is it important? Because as a linear transformation, we can split in this way. Yeah. And now you see this vector is already given and this vector is given, right? So I can do the calculation now. I just replace this, the second vector, the last one is given in the last spot, which is this vector. So now one vector minus the other vector, you'll get this as your final answer, right? And this vector means what? This is the vector for this one, which is the column 2 of matrix A. Yeah. So now to look at the whole thing together. Yeah. I think we know the whole matrix A already. Yeah, the matrix A got the column 1. Please look at the column 1 up there, which is this one. And the column 2 is this one. And the last column is already automatically given, which is 10, 10, 9, 8, right? Yeah. So that's a way to find the standard matrix to represent the linear transformation. Yeah. Yeah, so as a last exercise, let's do this one. I'm giving you a linear transformation such that it is mapping two-dimensional domain to a two-dimensional codomain, and these two maps are given. So are you able to tell me what is the standard matrix A to represent this linear transformation? And if you have been following what we have been doing up to now, the fact is that T is a two-dimensional domain mapping to two-dimensional codomain, and the matrix A must be 2 by 2 now in terms of size. And the A must follow this fact, where the column 1 must be the same as T of 1, 0, and column 2 is the same as T of 0, 1, right? So now it means that you have to compute T of 1, 0. This is not given. So what can we do? And you have to think a little bit now. I think that we have to look at the given two values. I mean, one vector is 4, 3, the other vector is 1, 1. So maybe vector 4, 3 minus vector 3, 3 would be what we want, which is the vector 1, 0, right? And now please check. It essentially the same as vector 4, 3 minus 3 times the vector 1, 1 equals our vector. And why am I doing it like this? Because I need to look at the vectors which are already given. I mean, I'm talking about the fact that the the value of the map T for these two vectors are already given. Yeah, so that's the key. Yeah, so that's why I've been looking at these two vectors. And now, why is this fact good? Because we can think of the vector now as T of 4, 3 minus 3 times 1, 1. And because the map is linear, it means that we can compute the whole thing this way. Yeah. And T of 4, 3 is given, right? Which is the second vector here, which is minus 5, 0, minus 3 times. This vector is 4, 6. Yeah. So you can do this calculation yourself. So it's a simple task now. I think the vector is like this. Yeah. This is our column 1 for the standard matrix A. And similarly, how to get it done for the second one, which is T of 0, 1. You have to think a little bit, and honestly such thing has no shortcuts. Yeah, so maybe I think one way is we can think of it as 4 4 minus 4 3 is the same as 4 times 1 1 minus 4 3. This is the same as the vector we want, which is 0 1. Yeah, so it means that we can compute it now, yeah, by using this fact. And because the map is linear, it means that it is 4 times t of 1, 1 minus t of 4, 3. And 4 times t of 1, 1, you see t of 1, 1 is given, which is 4 times minus 5, 0. And minus t of 4, 3 is given. Oh, I'm sorry about it. So it's my bad. Yeah, so I read it wrongly. So actually, t of 1, 1 is the vector 4, 6. Yeah. So it's like 4 times 4, 6 minus t of 4, 3. T of 4, 3 is minus 5, 0, right? So you see it's like 16, 24 for the first vector. The second one stay the same. So you can do the arithmetics now. So I think the first spot is 21. The second one is 24. Yeah. So you see, this is the column 1. This is the column 2. So now let's complete the calculations. Basically, the vector that we are looking for must have this form. Yeah, yeah. And that's the end of this video.